The in-it-pen problem examines various revenue management strategies. Part A asks us what the booking limit for the discount or low-fare rooms would be, given that 50 rooms are protected for full price. That's equal to the capacity of the hotel minus the protection level quantity. We know that the hotel has 150 rooms available, and we've said that we've protected 50 rooms, and therefore we can allow up to 100 bookings at the low fare. Part B, finding the optimal protection level for full price rooms. Let's calculate a critical ratio. First, the underage costs, which are basically the costs of having too few high-price rooms, is equal to 200, the revenue from a high-price room, minus 120, the revenue at a low-price room. That's equal to 80. The overage cost is equal to an unsold room at the low cost, or 120. Therefore, the critical ratio, which is CU over CU plus CO, is equal to 0.4. If we look this up in standard normal distribution function table, we see that this probability corresponds to z-values between negative 0.26 and negative 0.25. We'll use the roundup rule and therefore compute a z of negative 0.25. Now, evaluating this in our quantity formula, which is mu plus z times the standard deviation, we know that the high-price rooms are normally distributed with a mean of 70 plus a standard deviation of 29 times that z of negative 0.25, and we get an answer of 63 as the optimal protection level for full-price rooms. Moving on to Part C. If the Sheraton were to force the in-it-pen to decrease its business traveler price to $150, this would decrease the number of the optimal protection level. The reason why is that the lower price leads to a lower critical ratio, and therefore, like I say, a lower protection level. The reason why it's less valuable at this point to protect rooms for the full fare, given the relationship between that 150 less 120 and 30 as your underage cost and your overage cost of 120. So it would decrease. For Part D, what number of rooms remains unfilled if we had a protection level of 61? The number of unfilled rooms is the same as expected leftover inventory. So let's start out by creating a z-value corresponding to this number of protected rooms. So 61 minus 70 all over 29 equals a z-value of negative 0.31. From the standard normal loss function table, we know that this has a corresponding L of z that's equal to 0.5730. Therefore, expected lost sales, given by the formula of the standard deviation times its L of z, is equal to 29 times 0.5730, which comes out to 16.62. The expected leftover inventory, therefore, is equal to the number of rooms that we've protected, 61, minus the mean demand, plus the expected lost sales. That equals 7.62. So that means that we can expect 7.62 rooms to remain empty. Parts E, F, and G will be answered in Part 2 of this video.